All right, let's dive into something that is famously one of the weirdest topics out there, but at the same time, it's the engine behind almost all of our modern technology. We're talking about quantum mechanics. It is, without a doubt, the world's most absurd and somehow its most successful theory ever. To really set the stage here, let's start with a quote from the absolute legend Richard Feynman. He said, "Quantum mechanics deals with nature as she is, absurd." And trust me, he was not kidding. We are about to see just how unbelievably strange reality gets when you zoom all the way down to the tiniest scales. So, to get why this was such a huge revolution, we've got to travel back in time to the late 1800s. Back then, physicists were feeling pretty good about themselves. They thought they had pretty much everything figured out. Their classical physics was this beautiful, perfect machine that could predict everything from the orbits of planets to how to build a bridge. But then some little cracks started showing up in that perfect theory. And here's the heart of the problem. You see, the world we live in, the classical world, it makes sense. It's predictable. You throw a ball, it follows a smooth, continuous path. It's intuitive. But the quantum world, the world of atoms, electrons, and photons, well, that place plays by a completely different rulebook. It's all about probabilities, things come in little packets, and honestly, it's just deeply weird and counterintuitive. The first really big crack was this thing called the black body radiation puzzle. Basically, the old physics made a prediction that was just spectacularly wrong. It said that any hot object, like a glowing piece of iron, should be blasting out an infinite amount of energy as ultraviolet light. They even called it the ultraviolet catastrophe. The only problem? When they actually did the experiments, they saw the complete opposite. Theory and reality were in a total showdown. And this is where it all begins. To fix that puzzle, a physicist named Max Planck came up with an idea that was so out there, so radical, it shattered an idea about the universe that had stood for centuries. So back in 1900, Planck suggested something crazy. He said, what if energy isn't like a smooth, continuous river? What if it's more like a stream of tiny, individual water bottles? He called these little energy packets quanta. Think of it like this. You can't have just any amount of water. You can only have it in 1 bottle, 2 bottle, or 3 bottle amounts. It was a bizarre idea, but guess what? It perfectly fixed the black body problem. But an idea is just an idea until someone proves it's real. And who stepped up to the plate? None other than Albert Einstein. In 1905, he used this quanta idea to solve another puzzle called the photoelectric effect. The mystery was why, when you shine a brighter light on metal, you get more electrons flying off, but not faster ones. Einstein's brilliant insight was that light itself must be made of these energy packets, which we now call photons. A brighter light just means more photons are hitting the metal, each one knocking out a single electron. It was a total game changer. Okay, so energy comes in packets. Light comes in packets. So what about matter? What about the atoms that make up everything? The next big step was to see if these weird new quantum rules applied to the atom itself. Let's play a little thought experiment that actually happened, and it led to a totally shocking discovery. What do you think happens if you shoot a beam of silver atoms straight through a magnetic field? Classical physics has a very clear, very simple answer. The classical prediction? Well, you'd expect the atoms to act like tiny spinning tops, getting deflected every which way, creating a continuous smear on a screen at the other end. But that is not what they saw in 1922. Not even close. Instead, the beam of atoms split into two separate, distinct beams. That's it, just two. There was absolutely nothing in the middle. According to the old physics, this result was just impossible. So to explain this, scientists had to basically invent a whole new property of matter. They called it spin. It's not really spinning like a top, but it's a fundamental property just like charge or mass. And the key thing is it's quantized. For those silver atoms, their spin could only be up or down. Nothing else was allowed. And that's why they saw two distinct beams. Matter itself was playing by these weird, discrete quantum rules. All right, so things coming in little packets is one thing. That's strange enough. But now, we're about to take a turn into the really, truly mind-bending stuff. Welcome to Uncertainty and Duality. So, at the very heart of all this quantum weirdness is a concept called wave-particle duality. And it basically says this:
Tiny things like electrons, well, they're not really particles, and they're not really waves either. They are somehow both at the same time. And which one they decide to be depends entirely on how you decide to look at them. Yeah, reality itself has a built-in identity crisis.
So, to wrap your head around this, let's picture the most famous experiment in all of physics. First, imagine you're shooting tiny marbles through a wall with two vertical slits in it. What are you going to see on the screen behind the wall? Easy, right? Two bands, right behind the two slits. Simple. Okay, part two. Now, instead of marbles, imagine sending a water wave towards those same two slits. What happens now? Well, the waves go through both slits, and the new little waves on the other side interfere with each other. They cancel out in some places and build up in others. You don't get two bands, you get a whole complex pattern of many bands. This is the classic signature of a wave. Now for the shocker. What happens when you fire electrons? One single electron at a time at those two slits. You'd expect them to act like the marbles, right? Creating two simple bands, but they don't. After you fire enough of them, you get the wave interference pattern. This means each individual electron, all by itself, seems to go through both slits at the same time and interfere with itself. This is nature just being flat out absurd. This deep strangeness leads us to another one of the fundamental rules of the quantum world, laid out by Werner Heisenberg back in 1927. His famous uncertainty principle basically says there's a hard limit on what we can ever know about the universe. Here's an easy way to think about it. If a police officer clocks your car's speed with a radar gun, the radar signal technically bumps into your car and changes its speed, but by an amount so tiny it's meaningless. But in the quantum world, the little photon of light you'd have to use to see exactly where an electron is would be like a bowling ball hitting it. It would completely change its momentum. The very act of measuring one thing fundamentally messes up the other. There's a cosmic fuzziness baked into reality itself. Okay, I know what you might be thinking. This is all fascinatingly weird, but so what? Does any of this actually matter in the real world? Oh, you have no idea. It turns out all this weirdness is the absolute foundation of our modern lives. And before we get to the tech, we have to mention one more piece of what Einstein called spooky action at a distance. It's called entanglement. You can link two particles together so that their fates are tied, no matter how far apart they are. Billions of miles, doesn't matter. You measure the spin of one, and you instantly know the spin of the other. It's real. And it's the key to mind-blowing future tech like quantum computing. And all of this brings us right back to you, right now. Why does this matter? Because that smartphone in your pocket, the computer on your desk, even the USB drive you use, they are all powered by these bizarre quantum rules. Transistors, the tiny switches that are the brains of all electronics, they only work because of quantum mechanics. Same for lasers, MRIs in hospitals, you name it. None of it would exist without this theory. So we end up right back where we started, with absurdity. The solid, predictable world we think we live in is just the surface. Underneath it all is a foundation built on pure probability, uncertainty, and quantum weirdness. This theory, the most powerful and successful in the history of science, proves that reality is fundamentally stranger than we could ever have imagined. And that leaves us with one last big question. If this is the stuff we already know, what other unbelievable secrets is the universe just waiting for us to find?